Hi all, my name is Yannis Kasdaridis and I will present your demo with title The ICARUS Mote, a blowing off chip RTC to attain 22 nanoamps sleep current in duty-cycled IoT devices. This is a joint work with my colleagues Nikos Sideropoulos, Ioannis Zografopoulos, Polychronis Simeonidis and my professor Thanasis Korakis. In this work, we demonstrate the ICARUS Mote, the first mode that draws the outstanding current of 22 nanoamps in sleep state. The ICARUS is built around the STM32L476 MCU, while it features an XP footprint for plugging in wireless interfaces, while several other sensors are integrated on board. Moreover, the ICARUS features the RV1805 real-time clock. The RV is an ultra-low power IC that draws only 22 nanoamps. By exploiting this IC, we can control the go-to-sleep and wake-up phases of any IoT device. More specifically, we propose two topologies. In the first topology, the power switch, we employ a load switch that turns on and off the power of the entire node in a power gating fashion, while using the RV1805 RTC to drive the load switch. Users can configure the desired duty cycle in their application by programming the RTC. In the second topology, we apply the power gating method only for the sensors and the peripherals of the ICARUS node, while the MCU is configured to sleep in the lowest possible sleep state. In this topology, the RTC provides interrupt signals to trigger the MCU when in sleep. In our first experimentation scenario, we have configured the RV1805 to provide interrupt signals every 5 seconds, as illustrated in the oscilloscope. In the second scenario, we have configured the ICARUS mode in the power switch topology. When in sleep mode, only the RV1805 and the load switch are powered, thus the overall node's consumption is roughly a few nanoamps. We measure the current draw of our device using the current ranger meter as shown in this video. The trade-off presented when our principle is applied is the notable increase of the time required for the MCU to wake up. In the case of the power switch topology, the MCU requires roughly 4 milliseconds to wake up as measured using the oscilloscope. In the next scenario, we configure the ICARUS mode in the interrupt topology. In this topology, the MCU remains powered, thus it also drains a few extra nanoamps as shown in current ranger meter. In this setup, the RTC is used to provide interrupt signals to awake the MCU. Apparently, in this configuration, the wake-up time is much less as measured with the oscilloscope. We repeat the same experiment, but this time we configure the MCU in a different sleep state. Specifically, we use a state that supports memory retention capabilities. Despite presenting increased power draw, this sleep state supports ultra-fast wake-up of 7 microseconds. Lastly, we calculate and plot the life expectancy of the ICARUS mode in the different proposed topologies versus the life duration using the standard features. We note a significant lifetime increase when using the power switch topology in low duty cycles. Similarly, the interrupt topology features notable lifetime increase both with and without RAM retention capabilities. The impact of our principle has notable effect even when in higher duty cycles.
Thank you for your attention.